So where we're at is the capstone. We've worked through all the problems, I think. Remember, it's due tomorrow. That's the 4th by 11 a.m. That's in the morning. Okay? You're going to upload it to the Dropbox in D2L. Some of you already have. The reason I'm writing that again is because in D2L, under Cons 10, under the Capstone Project, I'm going to post solutions, and I'm going to post them about 11:30 a.m. tomorrow. So that's something that you can go back and look at, not just so you know what you did on the capstone, because if you did what I told you to do, your capstone should be in good shape. The reason for that is that you want to look at that before you take the final, right? Because there's some questions that come off of your capstone to the final, and they've made a multiple choice. You know, the same kind of stuff you were doing there, all right? That's the reason you want to go look at that. Like I said, if I can remember when I go back upstairs at 9 o'clock tonight, I'm thinking 11:30 tomorrow, okay? And then our final is on Thursday, the 10th, from 6 to 8. Little different change in time. I'm following the university's schedule. That's next Thursday from 6 to 8. And remember, Johnson City, Sam Wilson, 521, you're going to Gilbreth. 306. Rob, you there?
Yes, sir.
You're going with them, correct?
Yes, sir.
Okie dokie. 531. You folks here, you're going upstairs to room 336. That's the computer lab, right? Upstairs in the corner. 990, the streamers. If you told me Johnson City, you're going to Gilbreth. 106. And there'll be some straggly bearded guy there with you. If you're coming to Kingsport, you're going to go with everybody else. Everybody will fit in the same spot there. And I think there's only one of you. You're going to room 336. Now, if you're using a proctor, obviously, I'll be sending the test out sometime Wednesday, probably Tuesday evening. You're going to do that. Now remember, if you're using a proctor, you will not enter your answers in D2L. That's the only group. Everybody else will be sitting at a computer. When you're done, you're going to log in. You're going to go to evaluation, assessment. You're going to pick your form. You're going to go in, pick whatever letter for each one of them. At the bottom, submit. It'll immediately grade. It'll show you your grade. You'll know what you made on the final. Okay? Now, you folks need to bring an ID and a calculator. The ones that are using a proctor, you need, I'm assuming wherever you're using it, you needed an ID, you need your calculator, and you need your tables and formulas. I'm not going to email those to your proctors. So one more time, in D2L, you're going to go to evaluation when you log in. You're going to go to assessments. You're going to pick the form you got. And right on the front of the test, you'll see when you, because I posted some old finals for you, you'll see that says Form A or Form B or Form C. You'll put it in, okay? You'll just click that. The person that you're with will have the password for you because it's password protected, okay? You'll go in and put your answers in, be done with it. All right? Now, the other thing is I've posted old finals. They are in D2L, content, old finals. There's 3 of them. If I remember right, they're from the fall and spring of 2014 and the fall 2013. They're there. They're listed there for you, and then the answers are there, right? A, B, C, D, or E, whatever the answer is. All right. Now, the reason we put that up is that would be a good place to start studying for the final. I know we've covered all kinds of material. You've done homeworks for me. You got 2 tests for me. You got learning curve stuff and all this. You want to see what a final looks like, right? You want to see the style of questions that they ask and how they ask questions. The other thing you want to do is, when you're studying for this, is you want to take 2 of these and you want them side by side. And you want to see, you see that concept right there? It's the same on both of them. Maybe they changed what the variable is we're talking about, but the concept's exactly the same. I can take 2 of them and lay side by side and go through and match up the questions where we're asking you the same idea or concept there. So you definitely want to take a look at these old ones to get a feel for what they're asking you and how they ask you about the material that we covered, right? That would be a good starting spot. Anybody got any questions about the final? Because, look, this is our last night. You're not going to hear from me again. Again, I'll post what room you're going to and stuff on the home page of your D2L there, if I can remember to do that. All right? I think we got everything covered. All right? Capstone, final. Everybody's going everywhere. We're going to run all over the place. What I want to do tonight is kind of finish this material up. All right? So where I was at the other day was I was like on page 490, and we were looking at 2 sample problems. And what makes it a 2 sample problem is there's 2 populations. You have 2 separate samples. There's no matching allowed. Your 2 samples are independent. Just because you know what's going on in sample 1 doesn't tell you anything about the people or whatever's going to be in sample 2. Okay? And then the last thing I wrote up was this idea of this 2 sample T statistic. So we're still dealing with T-scores here, even though you've got 2 of everything running around. And I wrote it as you're going to look at the difference of the 2 sample means. I'm going to put a little 0 there. Normally we don't write that 0 there. That's the difference of the 2 population means. It turns out it would be 0. And then you're going to divide by something that looks like this. Now, that's the standard deviation from the sample 1 over the sample size from of a population 1. Here's the standard deviation squared. This is a standard error again. Right? Because we're estimating the population standard deviations. You're never going to use that. I don't even care if you get out of this class, you'd never use that. And if you're in a class and somebody's making you use that, there's something definitely wrong. Right? At this point, you've got to be using the software. Now, the reason I wrote that up is, that's a T-score, right? Does not have exactly a T distribution. The ones from before did. So it's not exactly a T. But in practice, in the real world, a T distribution is very accurate. So it may not be exactly a T distribution, but it's close enough that we're going to use a T distribution. Going back to Tuesday with you, or hell, it could have been last Tuesday, the Tuesday before. Anytime you're telling me you're working with a T distribution, you always have to tell me which one you're working with, because there's a whole bunch of them, right? There's a family of them. There's one for every sample size. There's one for every degree of freedom. Okay? So, I'm going to give you 2 options for which T distribution we would be using. There's 2 options on how to figure out the degrees of freedom. One is let the software choose. That's always the best choice. That means I'm not doing anything by hand. And 2, okay, is use the degrees of freedom, which is equal to n minus n, the sample size 1 out of population 1 minus 1, or let the degrees of freedom be the sample size of sample 2 from population 2 minus 1. You want the smaller of those two. That's what you want. Now, before I do a problem here, all right? When I think about these, and I'm thinking about, a confidence interval. Look, I'm on page 490. There's a box there, and there's a big old formula for the confidence interval. I'm not going to write that down. What I want you to realize is the confidence interval is estimating the following. The difference of the two population means. Not the mean of the differences, the difference of the two population means. That's what the confidence interval would be estimating. All right? And when you're doing a test that's a two-sample problem, the null hypothesis is always that the two population means are equal. So if you look at the difference of the two population means, that means it's 0. I always write it like that, but it can also be written like this. Right? If mu1 is equal to mu2, that means mu1 minus mu2 is 0. I always like the fact when I'm looking at a two-sample problem and somebody wants me to do a test of significance about these two population means, I like writing the fact down that the mean of population 1 is equal to the mean of population 2. Okay? What does that mean to us? Well, the alternative hypothesis is always one of the following. Greater than, less than, they're not equal. You've either got a one-sided test to the right, one-sided to the left, or a two-sided test. That's the way I always think about these, right? Is the null is they're equal. The alternative is one's greater than the other. This one's less than that one, or they are different from each other. Okay? Now, again, before I do a problem, on Tuesday we had talked about the sample size that was needed to trust your p-value or your confidence interval when we were looking at just a single sample, right? The one sample t-statistic. And that was on page 470. Remember, if your sample's between 2 and 15, when you look at the data, when you look at the histogram or stem plot, you can't have any skewness and any outliers, right? Or you don't trust this. Between 15 and 40, we can get away with a little bit of skewness, still a little outlier, but it can't be a bad extreme outlier. If your sample size was bigger than 40, the most important thing was not what the data looked like, whether it had outliers or skewed. The most important thing was that you had a simple random sample. Remember that? Page 470 in your book. Little box there, I pointed that out to you. Well, page 470, again, when can I trust? Look, I'm going to use the term robustness of the two-sample T procedures. Right? Where we're looking at two populations and two means. Robustness means how much can the conditions be violated and still trust your confidence interval and still trust your p-value. That's a freaking statistician's term, robustness. I want to know what I can get away with. Oh, wait, how bad can the data be and me to still do the test and trust the p-value? How bad can the data look and me be able to still do the confidence interval and trust my confidence interval that it's halfway accurate? Statisticians say robustness. They don't like the term, how much can I get away with? All right? So what you do is you replace sample size with the sum of the two samples in your two-sample problem. Now, the reason I put page 470 again, I still got that same box in my mind. So if I'm between 2 and 15, where I added the two samples together, you can't get away with anything in either population. If you're between 15 and 40, and you've added the two populations together, right, their sample sizes out of those two populations, and you're between 15 and 40, you can get away with a little bit of skewness and no strong outliers. If you add your two sample sizes together and you're bigger than 40, the more important thing is that you had simple random samples from your population. The skewness and stuff doesn't matter. All right? So what I would like to do is, look, I'm not overly concerned about this chapter. Look, there's nothing on your project about it. I think one problem will suffice. All right? So what I want to do is I'm going to come over here, and I'm going to look on page 497, and I'm going to look at this problem 21.9. All right? It says, do good smells bring good business? Businesses know that customers often respond to background music. Do they also respond to odors? One study of this question took place in a small pizza restaurant in France on 2 Saturday evenings in May. On one of the evenings, a relaxing lavender odor was spread through the restaurant. On the other evening, there was no scent was used. Did you guys know that lavender was a relaxing odor? No, my wife, I went home I got to tell a story. I know it's last night. I got to tell a story. One night I go home and there's something in the house. I'm a sniff and I'm like, what the hell's that odor in the house? And she said, oh, didn't you know that's lavender? That's a relaxing odor. I'm like, do I look relaxed to you? And she said, no. I said, well, maybe it doesn't work on me. You should get it out of the house. So lavender's a relaxing odor for some people. Okay? It says table 21.2, page 498, gives the time in minutes the two samples of 30 customers spent in the restaurant and the amount they spent in euros. So it does there's two things measured here. How much time the customer spent and how much money they spent. And obviously there's 4 columns, right? How much time, how much they spent, lavender odor, how much time, how much they spent, no odor, right? So there's 2 variables here. I'm only going to be interested in one of them, and it's whatever's in part A, and I'm going to be interested in the time, right? So what we want to compare is the time they spent with the lavender odor and the time they spent with the no odor, all right? So it says the 2 evenings were comparable in many ways, weather, customer count, and so on. So we're willing to regard the data as independent SRSs from spring, Sunday, Saturday evenings at this restaurant. That's our key, right? You know why that's key? Because you have one sample that's 30, and then you have another sample that is 30. Let's say they had the lavender odor here and they had no odor there. Notice, 30 plus 30 is 60. Am I bigger than 40? Life is good, right? Your combined sample size is large enough that what things look like don't matter. What was more important is that you had a simple random sample from this population, the population of people that had the lavender odor, and from the population of no odor. You got a sample of 30. Look, they didn't have to be equal. It just turns out in the problem they were equal. Hell, you could have had 30 and 45. You could have had 30 and 50. This problem, they're equal. It says, the authors say, therefore, at this stage, it would be impossible to generalize the results to other restaurants. Well, of course it would. At least at that restaurant, you can say something. You're not going to say something about a restaurant in another country or anything. It's all based off of that restaurant, so you can draw some conclusions about that restaurant, what they should be doing, right? So Part A says this. Does a lavender odor encourage customers to stay longer in the restaurant? So again, I'm going to use L for lavender. I don't even need to write that. Hell, you can see that. But what I'm going to do is I'm going to let mu, and I'm not going to subscript 1 and 2. I'm going to subscript with an L here. Mu sub L is the mean time in the restaurant. I'm just going to make it real simple for us. Mean time spent with lavender odor. Okay? And then I'm going to have mu with a little n. That's your mean time spent with no odor. Okay? I just want to, every time I do a two-sample problem, since there's two means, I got to keep track of what's what here. So, mu sub L, that's the mean time spent with the lavender odor. Mu sub N is the mean time spent with no odor. And then the question says, does a lavender odor encourage customers to stay longer in the restaurant? They want you to do a test of significance. Well, I already told you that the null is the two means you're looking at are always equal. Well, the question tells you about the alternative. And in this case, the question says, does a lavender odor encourage customers to stay longer in the restaurant? That would mean the mean time with the lavender odor should be greater than the mean time of no odor, right? That's what the question's asking you. So you're asked if the mean time of the lavender odor is greater than the mean time of no odor. All right? It says examine the time data and explain why they are suitable for two-sample T procedures. Use the two-sample T test to answer the question posed. Okay? So I'm going to come over here, and I'm going to find this. What file goes with this? Is the file there? Odors. What chapter is this? 21? Now look, that's just the table that's in the book there, right? And we're going to work with the minutes. So I'm going to go to Stat, Basic Statistics, two-sample problem now, right? Because you've got two populations, there's two samples. This is a two-sample problem here. You're trying to compare those two means. I'm going to click there. Now, I got both samples are in one column. That's not true, is it? No, the samples are separated, right? So I've got each sample in its own column. Now, you see where it asks me, where's sample 1 and where's sample 2? If I remember right, whatever one I put in first, that's... You see how I got the lavender odor first? Whichever sample, that should be that sample, right? So that it matches up with this, I'm going to come over here and I'm going to say, oh, I want the minutes with the lavender odor. And for sample 2, I want the minutes with no odor, right? Remember, I'm looking at minutes. Nothing about money spent. I'm going to come over here and I'm going to look at options. Now, forget the confidence level. Forget the confidence interval for a second. I'm interested in what's my alternative here. You notice the hypothesized difference is 0, right? That they're equal, right? It always stays like that because remember, the null hypothesis is always they're equal. That means mu1, mu sub L minus mu sub N is always 0. And then what do I want here? I want the difference of to be bigger, right? Mu sub L bigger than mu sub N. Now, I'm supposed to examine the data, especially when the samples are small. I'm going to examine the data here because it's something I want to talk to you about. I always come over here and I always want a box plot. It'll give me a box plot of both samples, right? I like this for a couple reasons. So on the left, that's the box plot of the minutes spent with the lavender odor. On the right is the box plot spent with minutes with no odor. Now, look at the minutes with no odor. What would you tell me about the shape of that distribution? You see how the median is about in the middle of the first and third quartile? Roughly symmetric. Look at the one where the minutes to lavender odor. You see how the median's closer to the third than it is the first? What's the shape there? That's a little bit skewed to the left, yeah? Does that matter? No. You put them together, 30 plus 30, 60, you're bigger than 40. It was more important that we had simple random samples, and they said consider them to be simple random samples. Now, you see the little lines? You see the little X's in the boxes? Those are the means. Remember, we're looking to see if one mean is greater than the other. Does it look like the mean of the minimum of the minutes for the lavender odor is greater than the minutes for no odor? You see how it's up here and you're down here? You see there is a difference between them, yes? Everybody see that? That's the reason I like this picture. Oh, hell, you understand, the further we're like this, the more significant the evidence is, the more you believe the alternative. The closer they are, not so much evidence. I'm trying to get you to see in the picture that when I see something like this, I'm going to get a p-value from your test. It's covered up now, right? It already did the work for us. The p-value is sitting there looking at you. You understand, the further they are apart like this, do you expect, when I start moving them like this, the means, right? Do you expect the p-value to get smaller or larger? As I go this way, the p-value is going to get smaller and smaller and smaller, right? As I get closer and closer, the p-value gets larger. Because when they're like this, there's not a lot of difference. When there's like this, there's hells of difference, right? So I see a difference here. Yeah, I see they're not close. I see there's a difference. Now the question is, are they significant? The question is how small is your p-value? Well, we move this little guy over, and then, look, this did all kinds of work for us. I'm going to get rid of this. I don't need that anymore. I screamed at you about that. Okay? Look, it says the two-sample t-test for in-confidence interval for the two samples. Look, it tells you the sample size for each one of them, the means, the standard deviations, and each one of them has a standard error. Remember, there's two of everything here. It says the difference is the mean of the minimum minutes of lavender. Remember, that was the first sample I put in. That's my mu sub L minus the mean of minutes of no odor. Forget the estimate for the difference. That's just the difference between the two means up there. That's 105.7 minus 91.3. Forget the 95%. You see the t-test? The t-test is the null was equal to 0. They were equal versus greater than, that the mean of the minimum, the lavender was greater than the mean of the no odor. The t-value here is 3.98. Is that large or small? Treat it like a z-score, right? That's your test statistic. That is gigantic, right? So back here, my t is 3.98. Remember, that's telling you the number of standard errors that this difference is from 0, from the center. And then, what's your p-value? My p-value is 0. Now look. You know it's not exactly 0. It's 0, 3 decimal places, or 4, whatever was back there. Right? You understand why I wrote these? 1, 2, 3, same as always. Okay? Now, what's number 4? You got a small p-value. What do you want to do? What's my standard statement when I have a small p-value? Reject the null and favor the alternative. What does it mean in the context of this problem? You got strong evidence. That lavender odor has people stay longer than no odor. So we go back to the question in the book. Does the lavender odor encourage customers to stay longer in the restaurant? And the answer is, yeah, you got a p-value of 0, right? Your alternative was that they stayed longer with the lavender odor than no odor. You have evidence in favor of that. Now, I want to do one more thing here, right? Because normally what I do is I usually don't talk too much about the confidence interval. I want to come back here. And remember, I told you, every time you use Minitab to calculate a confidence interval, and I don't care where I was, whether it was a 1 sample Z, 1 sample T, now I'm in a 2 sample T, to get the confidence interval, you always need to two-sided test. If not, you get some crazy and it tells you something about some upper bound and all that kind of stuff. Okay? So the only reason I did that, that's not going to change that. I'm interested in the second line up there. It says the 95% confidence interval for the difference, right? The difference of the two means is 7.17 to 21.70. What does that mean? We're 95% confident that the difference between the mean of the lavender odor time spent and the mean of the no odor is between 7.17 and 21.7 minutes. Right? We're 95% confidence that the difference in the mean of the time spent with the lavender odor and the mean time spent with the no odor is between 7.17 and 21.7. My statement is the same. Right? We're 95% confident the thing you were trying to estimate is in the interval that was calculated for me. What are you trying to estimate? You're trying to estimate the difference between the two means. It's always mu1, mu sub L minus mu sub N. The mean time spent with the lavender and the mean time spent with no odor. Right? That's the way this works. Now, you got 50 minutes to listen to my crap the rest of the semester. All right? I'm only going to do one problem there, right? My question is, you understand now, when you see a two-sample problem, and it's a test, they're equal. The alternative is greater than, less than, or not equal to. How do I know that? It comes from the wording of the question. The same way the alternative always happens here, it always comes from the question. And then the p-value is always the same. If the p-value is small, what do? You reject the null, you favor the alternative. Yes? I'm hoping if I say that enough times tonight, come next Thursday, when it's all put out there for you, and here's the test, and here's your p-value, and the frickin' p-value 0, you'll know whatever you want to do is, I don't believe the null, I believe the alternative. If I can get you to that point now, you should be able to pick out the correct thing that says, look, I got a p-value 0. I rejected the null. I'm in favor of the alternative here. Which statement tells me that I'm in favor of the alternative at that point? Because there's 72,000 ways I can write that. You know, okay, I like the alternative here. We believe the alternative. How do you want to say that? You have to pick out the one that says that. Okay? And then the only other thing I have for you out of this chapter is, remember, it's always about the difference between the two means, mu1 minus mu2. You're trying to estimate it with the confidence interval. You're trying to do the test of significance where the null is or equal, and then the alternative is one's greater, one's smaller, not equal to. Okay? Now, I do want to say a little bit about chapter 25 here. I have a reason for wanting to do it. You won't know till next Thursday, but I have a reason. Okay? So, chapter 25. Again, we're not doing anything by hand. It's all done on the computer. It's all going to have a printout for you. And I just simply call this the chi-square test. So, me calling it the chi-square test, that means it's the test of significance. It's the test of hypothesis. There is no confidence interval here. There's only this one test. Okay? And this test, what it does for us is this. If you want to know, is there a relationship? And I'm going to put a slash here. It's not always a relationship. Sometimes people will say association between two categorical So this is a story about two categorical variables. All right? And somebody's asking you, you see your two categorical variables, is there a relationship or an association between these two categorical variables? Well, then I have a question for you. When you're dealing with two categorical variables, how's the data come to us? Does anybody remember it's a two-way table, right? A two-way table. One of the variables is the rows, one of the variables is the columns. That's the way the data comes to you when you're looking at these two categorical variables measured on the same set of individuals. Okay? Now, I know there's an example 25.1 here. Look, I want to get to the point with this. So when somebody's asking you, the problem's asking you about, is there a relationship? Is there an association between two categorical variables? What you want to do is you want to perform a chi-square test. Should I write that down? They're all kicked back like they're having fun there. You want me to write that down? If you've got a two-way table and the question asks you, is there a relationship or is there an association or are these two variables independent, is another way to ask you the same thing. Because remember, if there's a relationship, they're not independent, right? If there is a relationship, if there is a relationship, they're not independent. If there's no relationship, they're independent, right? That's the same idea. So if the question asks you, are these two variables, these two categorical variables related, associated? What you want to do is a chi-square test. Okay? Now, here's what I want to do. Before I pull out a problem here. All right? Look, I expect you to read pages 577, 578, 579 is just a problem. I'm going over to page 581. Because when I have a two-way table, okay, when I'm looking at it, remember I told you there's a number of rows by the number of columns. There's 5 rows and 4 columns. It's a 5x4 table. I'm still back in chapter 6 with you, all right? The numbers that show up in that table are called observed counts. They are observed from the data. So if we're going to do a chi-square test, there's something called expected counts. Now, these expected look, you know how we always have like an X bar or a P hat as your data? No, the data is the expected counts here. Or, excuse me, the observed counts are your data. The expected counts have to be calculated knowing something. And the null is always, when you're looking at a chi-square test where you're looking for a relationship or an association, the null is no relationship. Remember, that means no association. That means the variables are independent. The alternative is, the alternative to no relationship is, what's the alternative to that is? There is a relationship. There is an association. The variables are not independent. They are related somehow. Oh, I know. I always write it in terms of mu is equal or p is equal, there's 2 of them, not here. There's way too, look, when I'm dealing with a two-way table, these are proportions, right? There's little p's there. There's not 1, there's not 2, depends on how big the table is. All right? That's the problem here. So when you're doing a two-way table and you're looking at these two categorical variables and you want to know about a relationship or not, it's just always stated. The null is there's no relationship. There's no association between these two. The alternative is, oh yeah, there is a relationship. There is an association. Okay? Now, assuming H naught is true. In other words, there's no relationship, right? We're going to assume that. We're going to calculate expected counts. Just like there is an observed count, every cell has an observed count, right? And what I mean by cell is, you're looking down, you're looking across, there's a number there. That's observed. Everywhere there's an observed count, there is an expected count there. Okay? And it's on the bottom of page 581. The expected count, now I'm just going to use EXP, is the row total times the column total. You understand, there's an expected count for every cell in the table. Every cell is in some row, and it's in some column. So you take the row total times its column total, and you divide by the table total, which we will know. So, if I have just for the sake of things here, okay? Let's say I have a 3 by 2 table. What that means is I've got there are 6 cells. 3 times 2, right? There's 3 rows, there's 2 columns. And so I just labeled them X sub 1, X sub 2. So that's cell 1, cell 2, cell 3, cell 4, cell 5, cell 6. It's always 3 times 2. It's whatever the rows times the column. There's a cell. So for each one of those little 6 numbers I have there, those are the observed counts. If we assume that the null hypothesis is true, that there's no relationship, there's no association, then we can calculate these expected counts. Okay? Now, I'm going to do it to you all at one point here, all right? What the chi-square test does it compares the observed counts to the expected counts. Okay, you've got these cells. Every cell's got an observed, every cell's got an expected. Remember, the expected is calculated assuming the null hypothesis is true. The chi-square test is going to compare in each cell the observed and the expected. The observed and the expected. The observed and the expected. And then you're going to add pieces together here. All right? So, where I'm at is, I am on page 583. The way it compares is what's called the chi-square statistic. You know how before we had a z-test statistic, we had a t-test statistic? When you're working with a two-way table and 2 categorical variables, and you're going to perform the chi-square test, you have the chi-square statistic. That's your test statistic here, okay? The way you calculate it is, now, you see that little funky X? That's your chi. It's not chi. That's chi. Little 2 up there means it's chi squared. Okay? What we're going to do is we're going to add a bunch of pieces together. You've seen me use that capital sigma before. It means add these things together. What you're going to do is you're going to take observed minus the expected. Now, you realize if the observed is bigger than the expected in a cell, that's going to be positive, right? If the observed is smaller than the expected, it's going to be negative. Remember, we don't like shit when sometimes it's positive, sometimes it's negative, so we are going to make them all positive by squaring it. And then we're going to divide by the expected count. The sum is taken, what are we adding up here? Is taking over all the cells in the two-way table. Okay? So that's what you're comparing here. That's what chi-squared, this statistic, is looking at. It's looking at the difference between the observed and the expected. Right? It's going to give you a number when you're all said and done here. The chi-squared statistic is just going to give you the number. The larger that number is, the further the observed and the expected counts in the cells are from each other. Okay? So, chi-square statistic measures, let's do it like this. It's a measure of how far the observed counts are from the expected counts. That's what it's measured. The further the observed and the expected, the reason I'm doing this is because I got a cell here, right? The observed and expected. The further they are apart, the larger that value is. The closer they are together, the smaller that value is as you go across the cells, right? So the closer the observed and the expected are together, the smaller the chi-square statistic. The further they are apart, the larger your chi-square statistic. Okay? Here's the punchline. Large values of chi-squared. So you get a large value for your chi-square statistic. That means that the observed and the expected counts are far apart. That is evidence against H naught. That means when you get a large value of your chi-square statistic, the expected and observed are far apart. You want to reject the null hypothesis. You want to favor the alternative. So when you get a large value of your chi-square statistic, the observed and the expected are far apart. You want to reject the null. You want to favor the alternative. What did you just find evidence of? Evidence of a relationship. Now, here's the part you got to wrap your head around. Look, I can always get you to say, I'm looking at a two-way table. I want to know if there's a relationship or association between these two categorical variables. The null is there's no relationship between them. The alternative is there's a relationship. So how does a large value of my chi-square statistic give me evidence of a relationship? Well, it tells you the expected and the observed counts are far apart. We had no control over the observed counts, right? That's what came from the data. Yeah, that was the original two-way table. Where did the expected counts come from? The expected counts came calculated. Remember, we had a formula, assuming the null hypothesis was true that there was no relationship. So what's wrong? The observed counts aren't wrong. What's wrong is the expected counts are wrong, yes? Because they're far from what's observed. Well, if they're wrong, how are they wrong? You didn't calculate them wrong. The problem was you assumed no relationship to calculate them. The catch is there really was a relationship. That's the reason the expected counts were so far off from what you observed. Okay? So a large value of your chi-square statistics is evidence against H naught. That's evidence of a relationship. What do you think about small values? The observed and the expected are close together. What's that? Small values. Of your chi-square statistic. That's the other side. Okay? Are not evidence against H naught. You didn't find anything. The expected and the observed are close together. This is what we were expecting to happen if there was no relationship. Okay? Now, again, before I do the software on you, there's a couple things I want to point out to you about this. Page 584. Cell counts required. These are cell counts required to trust the chi-square test. It says you can safely use the chi-square test with critical values from the chi-square distribution. Translation, I can actually use this when no more than 20% of the expected counts, remember the expected is what's calculated assuming the null is true, are less than 5. And all individual expected counts are 1 or greater. So again, here's the deal. You're looking at all these cells, right? And every cell's got an expected count. You count up the number that's less than 5, and you divide by the total number of cells. If that number is less than 20%, you can trust the chi-square test. That's what it's telling you. I don't even get carried away with the 2 by 2 test, because if it's 2 by 2, right, that means there's 4 cells. If one of them is less than 5, 1 divided by 4 is 25%, and you're screwed on your 20, right? So I just think about it in general. Count up the number of cells that have expected counts less than 5. Divide by the total number. If that is less than 20%, you can trust the chi-square test. Okay? Now, the other thing I want to do is this. There's something called a chi-square distributions. The S means there's more than one. All right? Now, the catch with these guys is they are a family of them, more than one. They always take positive values, and they are always skewed to the right. Anybody know what skewed to the right is at this point? That means you've got a tail going out to the right here. Okay? You specify a chi-square distribution, just like we did with the t distribution, by giving its degrees of freedom. Remember, with the t, it's always 1 less than the sample size. With the 2-sample t, if we're going to do it by hand, it was 1 less than the smaller sample size. The chi-square distribution has the degrees of freedom also. It's not the sample size. What it is r minus 1 times c minus 1, where r is the number of rows, and C is the number of columns. So if you have a 3 by 2 table, the chi-square distribution you're looking at would be, with degrees of freedom, 3 minus 1 is 2, 2 minus 1 is 1. You'll be looking at the chi-square distribution with 2 degrees of freedom. Now look, the only reason I bring this up, if there's a test of significance here, you know there has to be a p-value. And up till now, I've always showed you where the p-value is coming from, whether it was the standard normal, the t-distribution, it's always the area in the tail. One of these looks like this. Let's say this is your chi-square distribution. That's what they look like in general. They're always positive, right? They only have positive values underneath of them. It's skewed to the right. It's got a tail going out to the right. What lives under the chi-square distribution is this chi-square statistic. You know, just like what lives under a t-distribution? Hell, it's a t-score. What lives under the standard normal distribution? It's a z-score. It's a chi-square distribution. What lives under there? It's your chi-square statistic. The way the p-value is calculated is, see that right there? That'll be your p-value. Now, go back to a second. I told you a large value of your chi-square statistic was evidence against the null hypothesis, correct? You understand, the larger your chi-square statistic, the smaller your p-value, right? The less the area that's in the... I'm not telling you anything I haven't told you before. The large value of your chi-square statistic, the smaller the p-value, the stronger the evidence against the null in favor of the alternative. The smaller that is, the further it is to the left, the larger your p-value, you didn't find evidence against H0. Same story as before. Large value of your test statistic will produce a small p-value here. Okay? Now, I know I'm only hitting what I think's important here. All right? The other thing is this. You can go read this if you want. That's okay. If you don't want to read it, that's up to you. It's been like that all semester. There's not going to be any difference here. The books, if you read it, the book's going to talk to you about more than one use. Nah, shit. It's always a two-way table. It's always about association, relationship. Sometimes they'll talk about independence. And they'll even throw out the word a test of homogeneity. Look, we're checking to see if they're the same, right? That's what they're talking about. We're asking you if there's a relationship. We're asking you if there's an association. We're asking you if they're independent or not. I don't care what you call it. It's the same freaking test. Right? It's always the same. And it's always a two-way table. The other thing can happen is the data can come to us one of two ways. You can have a big, simple random sample and classify everybody by two categorical variables. You'll get a two-way table, yeah? You could have different groups and different samples, right? And then you classify the people by whatever variable you were measuring and the sample they were in. Is that still a two-way table? Yeah. Okay, you're in sample 1, you're in sample 2, you were in sample 3. Is that a categorical variable, what sample you came out of, what group you came out of? And the answer is, yeah. Hell, I don't know. It still looks like a two-way table to me. Whether it came from one simple random sample and you classified everybody by both, or you had different simple random samples and you classified everybody by the variable you're measuring and what sample they came out of. Okay, it still looks like a two-way table to me. And it's still a test of significance for the chi-square. All right? Now, here's what I'm thinking, all right? What I would like to do, just for the hell of it, is I'm going to pull your project back up. Now, the people that's already turned it down, don't freak out. The problem was there for us is the reason I like this. And I want to go back to this problem. Nobody was expecting you to put this on the project. Everybody understand that. So don't be uploading another one after you put that shit on there. Nobody was expecting you to do this. All right? Because we know that look, there's no class that gets to this chapter like 6 nights ago. It's always the last night, and we talk a little bit about it. And the weird thing is, you start taking like a biology class and stuff like that, this chi-square test will show up again. It actually show up in biology. It shows up in biology. Out of all of them, this might be the one you actually see in another class, other than the T stuff. You won't see that Z, right? You might see this one again. And the reason this problem is the way it is, you remember there's a 5F and there's a 5M here, correct? Now, we were going to let's look at this one. All right? It says, what variables we were looking at? We were looking at like age group and whether the government should require mandated childhood vaccinations, right? Yeah, that was the one we looked at. You made like a nice cluster bar graphs there, yeah? And so this is what I want to do. I want to come over here. I got that file up, and I would like to go to graph, bar charts. Remember, I got the raw data. I want clusters. Remember, I thought maybe the age group helped explain how you felt about the childhood vaccinations. Remember that? And then I also asked you to show Y as a percent and accumulate within that level. So what I'm going to show you is there's going to be two conditional distributions, right? There are going to be the conditional distributions for what the people said about required government vaccinations for the two age groups, right? So if I click OK here, right? Now, again, if I tell you something, you could have done it the other way. Nobody cares. It's okay. You could have went the other way, right? You could have had on the outside been what they thought about the child vaccinations, and the inside could have been the groups. But I'm looking here at two conditional distributions, the one on the left, the one on the right. The one on the left is conditional distribution of child here, given the age group 16 to 21. The one on the right is the conditional distribution of child, what they thought about childhood vaccinations, government mandated, given that they were over 21. Everybody got that? Okay? You posted, you actually, this is what the one you posted, I'm guessing back here, when it said make the graph. And then it said make the two-way table, and then you answered some probability questions based off of pulling the numbers off the table, right? There was an and, there was an or, there was some conditional probabilities here. And then I'm out here just one at the bottom. And it says, do you think there may be an association? Uh-oh. What the hell we just talked about with chi-squared? Chi-squared was asking you, right? That's what it's about. It's a story about you've got two categorical variables. Is there an association or relationship between them? Yeah? That's actually the language I just used on you in chapter 25. It says, do you think there may be an association between age group and child? Are those two categorical variables? Don't even answer. Of course they are. Hell, you just made a two-way table. You just made cluster bar graphs above that. Okay? It says, why or why not? Explain your reasoning based on what you see in your graph. See, they didn't want you to use the chi-square. Why? Because it's the last night and they knew everybody would be rushed and you'd be crazy people. So we just looked at the graphs, right? And if I come back over here and I look at these graphs, what they're asking you is do these two graphs look the same or do they look different? They look pretty much the same, don't they? So do you think there's a relationship? In other words, when somebody's asking you, you've got two categorical variables, is there a relationship between the two? Does it make a difference, the age group? Does that tell you anything about what the people thought about mandated childhood vaccinations? And the answer is no, because if it did, they would look different. Everybody understand that, right? They would look different here, way more different than this, if the age group mattered, if these two were related in some way. Okay? And that's what you told me. Remember, we talked about both of these in class that night we did these. Yeah, do I see anything? Yeah, they look about the same to me, right? I don't see any gigantic difference there. I'm assuming that's what you told me on your thing. So if I come over here and I get rid of this, let's say I want to do a chi-square test, because that's what this is begging for. And actually, that's the best way to answer this. When somebody asks you, you got two categorical variables. Association? I don't know. Hell, I need a chi-square test. Okay? So I'm going to come here to stat tables. Now, we've been there before, right? We've tallied individual variables. I showed you how to make the two-way table and everything, right? I'm going to come down here to tables, cross-tabulation, make the two-way tables, what that means, and the chi-square test. The rows, I can't remember what I made the rows last time. I'm going to think I made the rows the child. And I'm going to make the columns the age group. Okay? Now, if I don't do anything else, hell, that would just give you the two-way table. But you see down here at the bottom where it says chi-square? Okay? So I've got chi-square. I want to perform the chi-square test. I want the expected cell count for each cell. Remember, every cell's got the observed. That's the original two-way table. Every cell's got an expected, right? And then the only other thing I ever want is each cell's contribution. Because remember, a little chunk of the chi-square statistic comes from each cell. Remember, you do the observed minus the expected. You square it, divide by the expected, right? And I'm going to click OK here. Now, there is your tabulated statistics. The rows are the child, the columns the age group. You notice that looks like the two-way table you made for me, except, does everybody see where it says cell contents, count, expected, contribution? Every cell that you see there has got three numbers in it. The top number is the observed count. That's what came in the two-way table, the 120, the 38, the 540, the 116, right? That was the table you made me. Underneath that is the expected counts, 128.1, 29.1, 531.9, 124.1. And then under that in each cell is that little observed minus the expected, where you squared it and divided by the expected. That little chunk of the chi-square, the 0.51, 2.19, 0.12, 0.59, 0.5297. And then you see at the bottom where it says Pearson chi-square is equal to 3.366. That's your chi-square statistic here. That's that little guy I keep writing chi-square. It says your degrees of freedom is 1. Why is the degrees of freedom 1? It's a 2 by 2 table. 2 minus 1 is 1. 2 minus 1 is 1. 1 times 1 is 1. You're looking at the chi-square distribution with 1 degree of freedom. Your p-value here is 0.067. Is that large or small? That ain't small, right? I mean, you're not significant at the 5% level, are you? Do you have evidence of a relationship here? Do you have evidence of an association here? Do you have evidence that the two bar graphs look different? No, you don't have evidence here. Right? You don't have evidence of an association. You don't have evidence of a relationship. You don't have evidence that those two bar graphs look different, and that's what we decided. This would be the best way to answer that question, but since we didn't know the chi-square at that point, we did it looking at the graphs, and I told you. The graphs look relatively similar, right? Yeah, well, the chi-square test is confirming that for you. Now, the other thing to point out to you, take a look at the cell that says 16 to 21 age group and said no to vaccinations. You see the observed count was 120 there, yes? The expected count, assuming that there's no relationship between these two variables, turned out to be 128.1. Are they close together? Yeah. The 38 and 29 are close together. The 540 to 531 are close together. The 116 to 124, they're close together. So the chi-square statistic's small. The p-value is relatively large. You don't have evidence at the 5% level. Okay? Now, we got to come back here because not everybody did that problem. Some people did the one about, carrying arming military personnel in military buildings, and should those on welfare be required to pass a drug test? Let's do that one. Okay? If I come back over here, and I'm going to leave that, I'm going to put this back up here a little bit. If I want to go to graph, bar chart, counts of unique, I want the graph to start with. All right? If I click OK here, I want, what did I think it was? I thought maybe your military service helped explain what you thought about people on welfare having to take a drug test, wasn't it? Wasn't that the question? Yeah. So I'm checking to make sure I want to see percentages. I'm going to click OK. So now you're looking at two conditional distributions again. You're looking at the conditional distribution of welfare, whether the welfare folks should have to take a drug test or not, given whether people served in the military or not. Right? So the one on the left is military no, the one on the right is military yes. Do those two look the same or they look different? These look different, right? In other words, do these look more different than the previous set? And the answer is yeah. Okay? So, I'm going to get rid of that. You know they look different here, yeah? I want to do the chi-square test. I want to confirm, because I see a difference. I want to know if the difference is significant. I want to know if there's evidence of a relationship here. All right? So I go to Stat, Tables, cross tabulation chi-square. This time I want the rows to be welfare, and I want the columns to be military. Okay? And I'm going to check the chi-square. It should all still be set where I had it before. I'm going to click OK. I'm going to click OK. Now, the rows are the welfare, yes or no, they should be drug tested. The columns are military, yes or no service. Notice there's 3 numbers in each one of the cells again. The observed, the expected, the contribution to the chi-square statistic. At the bottom, there's this Pearson chi-square. That's our chi-square. It's 40.399. Is that large? We're getting bigger, right? The degrees of freedom is 1 because you got a 2 by 2 table. 2 minus 1 times 2 minus 1. Your p-value is 0. You got evidence of a relationship or not? The p-value being 0 means you want to reject the null. The null is there's no relationship. Here, you got evidence of a relationship. You got evidence of an association. You got evidence that those two bar graphs are different, which is what we were seeing, correct? Now, the reason I wanted to do this one, because I knew one was one way. You didn't have evidence against the null. And I knew the other one is, yeah, you do see it in the bar graphs, and the chi-square statistic is confirming that for you, right? This chi-square test. The p-value is 0. You got evidence of a relationship between military service and what people thought about welfare people having to take a drug test. Yeah? See, here's the problem with this chi-square test. When the p-value is large and the data is consistent with H not being true, in other words, you don't reject it, when the data is consistent with no relationship, there's nothing left to do. When the p-value is small and the test is telling you you got evidence against H naught, that you should reject the null, that you got evidence of a relationship, it doesn't tell you where the relationship is. It will just tell you if you have evidence of one or not. Everybody understand that? That's all it's going to tell you. It's not going to tell you where the relationship is. It's not going to tell you how the two variables are related. It will tell you whether they are or not. What you need to do is, we need to come back here, and what I do is I come back to the table, and I look at the contributions out of each cell to the chi-square statistic. You see the chi-square statistic here is 40.399. Does anybody see the cell that contributed 31.257 to it? Did that contribute a lot? It contributed 75% of it to it. So the relationship, whatever the cells, look, when you get a small p-value and you have evidence of a relationship, then you got to stop. There needs to be more done at that point. You just can't say, okay, I got evidence of a relationship. People's going to want to know where the relationship is. You go back to the printout. You find the cell or cells that have the largest contribution. It's not easy to pick. It's not hard to pick out here. 31 out of 40 in that chi-square statistic comes from the cell that had no military service and said no to drug testing for welfare, right? That's that first cell there. Now, once you identify the cell that has the largest, look at the observed and the expected. The observed count was 31 that had no military service and said no to drug testing for welfare. The observed was 11. Excuse me. The observed was 31. The expected is 11.8. That's a big difference. What's the problem here? There was way more people that said no military experience and said no to drug testing for welfare than we were expecting, yes? If there was no relationship. The relationship is, it looks like the people who don't have any military experience are more likely to say no to drug testing for welfare, yeah? That's where the relationship is. The cell that contributed the most. It contributed 31 out of the 40 for the chi-square statistic. Look at the observed and the expected. Here, the observed is much larger than the expected. Only 31 was observed and only 11 was expected if there was no relationship. There was way more people saying no military service and no to drug testing for welfare than we were expecting if the null hypothesis was true. You only got to do that when you reject the null. If you don't reject the null, there is no relationship, so sure the hell don't look for one. If the p-value is small, you reject the null, you have evidence of a relationship, now you got to tell me where it's at. You'll never tell me. You might have to tell somebody. I mean, we're done. Okay? Now, the other thing I wanted to do, right? So we know the capstone's due tomorrow. Please do not, please do not go back and put this shit on your capstone. And that was, I needed something to talk about. That was a nice problem for me to talk about. All right? Don't do that, okay? What we talked about before, without the chi-square, was perfect. The one, yeah, they look similar. No, they really don't have any. They look the same. This one here about military service and drug testing welfare, they look different. I can see they look different. Don't do the chi-square for me, okay? Everybody's happy. Now, the other thing I wanted to do, because you always want to know at this point, when I go to calculate your grade, here's the way it works. You're going to have, you've seen in detail D2L already. I've already put some things in there, right? Like the first two tests, I think. So you get some homework points, right? You notice every homework I've given back to you has been a number divided by a number, yep? Well, it turns out the number in the bottom, when I added them all up, was 132. There was 132 things I checked through the 9 homeworks that we've done all semester. You need to add all the tops together, whatever that is. I mean, you got 127, 132, whatever, 118, I don't know what it is. And you're going to take that and you're going to multiply by 250. Because remember, the homework's worth 250 points. So you're taking the proportion out of 250 that you got correct. The test 1 points, you're going to take, remember, you had a number over 40, right? Multiply that by 200. Test 2 points. You had a number over 40 times 200. You can make it real simple and just take the number that's in the top, the number you get right, and multiply by 5. We get the same thing. You've got the final. Again, that's going to be something out of 40. You multiply that by 200. What do I got there? 850. I've got the capstone project, and I think I labeled this CA. That's just a possible 100, right? It'll take me a little while to grade these. You'll have some number. You'll never get them back, right? All you'll do is you'll see your grade in D2L. I'm not going to send them all back and all that. Okay? And then we've got the learning curve. Remember, that's a possible 50. Does that sound right? So that's something out of 50. Now, if I add all these together here, don't I get my 1,000 points? There's 850, there's 950, there's 1,000, yeah? The learning curve works like this. Remember, we didn't do one of the 19 chapters. We did 18 chapters, there's there. So you're going to get 2.5 points for each one of those. If you did them all, those 18, you're going to get 2.5. And I'm going to start everybody with 2.5 because I didn't assign that other chapter. All right? So that's your 50. You've got the bonus for attendance. And the way that works is it's a possible 50. Right? Every time you missed a class, that took 10 away from those 50. You had a class survey. Remember, some of us, you gave me like the little picture. That was a possible 5. So I'm going to add them all up. All right, it looks like I got 1,055. And the scale's 1,000. And so what I do is I just add all your points up, and then I go to the syllabus, and wherever you fall, I'm giving you the letter grade and with the little sign, plus or minus. Now, here's the thing. Every time I get to the end of the semester, the number I always have in my head is 720 is a C and 719 is a C minus. Okay? That's just the one I pick out. And so before you start emailing me, telling me you need this, or you need that, or you need this, or you need that, and let's say you got like 716 points and telling me you need a B, you just get deleted. If you got 716 points and you're telling me you need a B, you don't even get a, normally I always respond. I can't give you a reasonable response at that point without being a smartass. So I just delete. Now, if you're at 716 and you see your grade, that's a C minus, right? But I've already looked at it. And what I've looked at is how many days of class did you miss? Did you do the learning curve? Did you do the class survey? Did you pick up those freaking extra 5 points you needed? So at the end of the semester, when we're all said and done, probably like next Friday or Saturday, and I send everybody an email that says grades are posted, you'll see everything in there. You'll see a total number of points. You'll see a grade. You got 716, and I gave you a C minus. That's because you didn't take advantage of all the points. Don't email me and ask me because we ain't moving. I've already looked at them. If you're within 5 points of the next change of sign or letter, I've already looked. I look at all of them like that. If you're at 750 and you're telling me you need a C plus, that ain't happening either. I mean, the C plus starts at 780, right? I mean, I feel like I've been fair all semester, and then at this point we got to assign a grade. So that's the way we play. All right? Anybody got any questions about anything? That'll be a no. I think we've got everything covered. Make sure you get your last homework back. Rob, when you're done tonight, will you send me the Excel file with the roll in it, please?
Hey, Mike.
Yeah?
I'm sending it to you right now.
Thank you.